How should NLP systems represent words? The simplest way is to use a unique ID for each word type. So cat might be 17, chef may be 91, etc. But there's no semantic information in the IDs. If two IDs happen to be close, the words are not necessarily similar. In this video, we're going to talk about ways of representing words using vectors of numbers, where the numbers capture some aspect of word meaning. We also call these embeddings, since we're embedding words into a vector space. Why do we want to represent words in this way? One motivation is to address issues that arise from the challenge of variability in natural language. If we can represent these three forms of the word really with similar vectors, then our NLP systems will be able to handle these variations even if they don't all appear in the label training set for the task. How should we actually embed words? We'll see many ways throughout the course, since embeddings are a fundamental part of using neural networks for NLP. But in this video, we'll focus on a very simple way based on the distributional hypothesis. It states that words that appear in similar contexts have similar meanings. The idea is often summarized in this quote from Firth: "You shall know a word by the company it keeps." Suppose there are 6 words that we want to compute vectors for, shown here at the top. The key idea is to have each dimension of the vectors correspond to some word that can appear in the context of these words. We'll use this set of 5 possible context words, so our vectors will have dimension 5. Then the entry in a vector is the number of times those 2 words appear close to one another in a corpus. Here's an example. Here are 3 sentences from Wikipedia containing the word chef. We'll be computing counts of the number of times chef appears with each of these 5 context words for various window sizes. We'll use W to denote the window size. When W is 1, we look at 1 word to either side of every instance of chef. Among our 5 context words, the word the appears twice in these windows, so 2 is the first dimension of the vector for chef. None of the other context words appear, so all other entries are 0. When we increase W to 4, now the appears 3 times, and cook appears 3 times as well. The window size is an important parameter of this procedure and can lead to different types of similarity being captured by the resulting word vectors. We use that simple procedure of counting context words, and that gives us distributional word vectors. 2 words will have similar vectors if they tend to appear with the same context words. Here are vectors using counts I computed from about half of English Wikipedia using a window size of 10. Now that we have word vectors, we can compute similarities. There are many ways to define similarity of vectors. One starting point is dot product, which is the sum over dimensions of the product of the corresponding entries for the 2 vectors. The dot product is going to be large when the 2 vectors have similarly large or very small values in the corresponding dimensions. Now that we have a way to compute the similarity of 2 vectors, we can compute the similarity between any pair of words in our vocabulary. For a given word, we can then rank the other words by similarity, and this is called computing the nearest neighbors of each word. Unfortunately, these neighbors don't look very interesting. Council is always the most similar word. Why is this? Looking again at the vector for council, it has the highest count for the context word the, which is also the most common context word for all the other words, so that term dominates the dot product. As a basic rule of thumb, we would like a word to be most similar to itself. This highlights an issue with dot product as a similarity function, namely that it does not account for vector length. Vector length is defined as the square root of the sum of the squared entries. So our solution is to instead use cosine similarity. Cosine similarity is simply dot product divided by the product of the vector lengths. It's called cosine similarity because it actually corresponds to the cosine of the angle between the 2 vectors. As such, it ranges from -1 to 1. If we recompute the nearest neighbors using cosine similarity, things look very different. Now the most similar word to a given word is itself, and in some cases the next few nearest neighbors also match our intuitions of word similarity. For example, chicken is similar to cooked and chef, and civic and council are similar to one another. Even with the use of cosine similarity, there are still issues with raw counts. The counts of common words like the are very large and therefore greatly affect vector direction, but are not expected to be very useful for most tasks. So there's been a lot of work in improving over counts. One method is TF-IDF, which is a classic method in information retrieval. TF, the term frequency, is just the counts we already computed, but we multiply it by IDF, the inverse document frequency. A word's document frequency is the number of documents containing the word, so the inverse of that is going to be small for the most common words. We often use measures like sentence frequency instead of document frequency, as well as various transformations of the raw frequencies, but we still just call it IDF as that's a standard term. Then our vector entry is the product of TF and IDF, which ends up downweighting the counts of common words. Another way to improve over counts is to use pointwise mutual information, or PMI. If we have two random variables x and y, PMI can tell us if two events, or values for those random variables, co-occur more often than if those values were independent. It's defined as the log of the joint probability divided by the product of the marginal probabilities for the events. If the events are independent, the quotient is 1 and the log is 0. If PMI is positive, the events co-occur more often than expected by chance, and if it's negative, they co-occur less often than expected. Now to apply this to word vectors, we can view the center word in the window and the context word as random variables, which each take on values given by word types in their respective vocabularies. Then we can estimate the joint and marginal probabilities using the single set of counts we already computed. To estimate the marginals, we just sum over the counts of one of the two random variables at a time. To get a sense for what PMIs look like, first we'll look at words with the highest co-occurrence count with the word chicken in Wikipedia. There are some content words here like chicken and fried, but mostly the top words are all function words. Now let's look at the words with the highest PMI with the word chicken. Here the list has no function words, it's entirely content words that have a semantic or a topical relationship to the word. Now let's get back to our word vectors. Here are our counts from before. Let's now replace them with PMIs. In all vectors, the PMIs with the word the are very close to 0, so those entries will have a much smaller impact than previously. And words with a stronger semantic relationship tend to have higher PMI. Now let's see how the nearest neighbors are affected by changing from counts to PMIs. Here, green words are those that moved up in the list while red words moved down. We generally find that using PMI works better than counts for distributional word vectors. And the basic idea underlying PMI has been applied in a lot of different settings in NLP, so it's a good thing to know about. Some work has found benefit from truncating PMIs at 0, calling this positive PMI, arguing that it's difficult to estimate anti-correlations or difficult to interpret. However, if we look at these negative PMIs, some of them do seem to be interpretable. Here are words with highest PMI with chicken, as well as those with PMIs close to 0 and those with the smallest PMI. The words with negative PMIs reflect different types of Wikipedia articles or articles about different topics, like the words museum and championship. So we may be able to model anti-correlations with negative PMIs, and I think the decision to truncate PMI at 0 should be an empirical decision we can tune just like anything else.